Okay, well, let's get started. Let's see, it's a little bit slow. Okay, I don't really know whether it's recording this one or recording the, I don't really know which screen is it. It's recording. But anyway, that's okay. Okay, guys. Yeah, today I wanna talk about this. Part of it for you, part of it for me. Actually, like I said, um, teaching is the best way for me to learn something new. And frankly, I've been teaching this PK stuff for a while, but I never really thought about like in details actually. So what I'm gonna do today is I'm gonna go over the very basic concepts, basically what I have been teaching, in the past 7-8 years, very quickly. I think if you guys took the PK class before, you probably learned this. But then after that, I wanna go deeper, basically, and to do, I mean, there's a lot more into this, and also I think one of the important thing for me is, previously I know how to calculate this using software. I mean, it's easy, anyone can do it, you just click a button, but exactly how it does that, frankly, I didn't know, but I figured that out by myself going through. So essentially now I can calculate all this using Excel without, using software. I want to show you guys how that happens. Okay, so why we want to study PK, right? So this is always the example I want to give. It's basically a mathematical definition of movement of drug, right? Going to inside, go out of the body. I mean, the most important thing is if you want to achieve pharmacology, if you don't have drug in your body, nothing can happen, right? And the simple example is coffee. We drink coffee every day. I know maybe some of you guys are kind of allergic to coffee, but I do drink this every day. I need to have this to keep me awake. Do you know the half-life of coffee, caffeine? 4 hours. Well, yeah, you remember. Okay. 4 hours, yes. So yeah, I mean, generally it's people say like 3 to 4 hours, something like that, right? I would say normal people. So then what does it mean? Every 4 hours, you drop your concentration by 50%, right? So you have a cup at 8 a.m. and then at noon, so you only have 50% of caffeine in your body, right? And then at 4 p.m., you only have what? 25, right? 50% of the 50, so that'll be 25. And then another, like at 8 p.m., you got 12.5% left, right? So generally for PK or for drug, after 3 half-life, people just think there's nothing left in the blood, or say, very minimal amount of drug, about 10%. And then we think that there's not much pharmacological effect, right? So that means if you have a coffee in the early morning, if you really want to stay up late, you probably need another cup, right? At the end of, yeah, so that's basically how to use this PK. So why we care about this, essentially we want to achieve optimal therapy, right? Because you don't have drug, nothing gonna happen. This is a key difference between, when people develop a compound that works in cell culture, right? In the plastic dishes. I always, say to make things work in the culture dish is a lot easier than to make it work in mice, because to kill cancer cells, you can just pour like sulfuric acid in there or whatever, right? So, or you just pour water in there, probably gonna kill the cells. But in animal, that's completely different story. So to have something work in cell culture, I would say the bar is relatively low, right? But to make it work in animal, that's a totally different story. But no question. Okay. But I mean, you guys can always stop me if I have questions. So this is we call this the journey of a drug molecule, and then everyone in the group heard about this ADME, right? Absorption, distribution, metabolism, elimination. This is the ADME. So basically, this is a general pharmacokinetics curve for oral drug, right? So you give the drug, you have this oral absorption process, and then it got, distribution eliminated. So this is generally what you observe for oral drug. For the IV drug, like IV bolus means like what Chen has been doing every day, right? So you inject the compound into the blood in a very short amount of time. So that's called IV bolus. Bolus means introduce something in large quantity in a very short amount of time, right? So like single injection. So intravenous, basically you introduce the drug directly into the blood, and there's no absorption whatsoever, right? So you instantaneously reach this so-called Cmax, right? Maximum concentration of the drug. Then what happens is you only observe this elimination phase, distribution elimination phase, right? So that's actually that's why a lot of our study we want to do the IV bolus injection, because that will just eliminate the variation of the oral absorption process, right? So we primarily focus on the elimination phase, basically. Okay. One question, right? So, I mean, we can get drug from the plasma, right? But there's tons of albumin protein in the blood, very high concentration. So which form is the active drug? Is it a albumin bound form or free drug or both? Free, right? So I think you guys should know this. This is so-called free drug hypothesis, which we'll talk about later. But then when we do the measurement, what do we measure? Is it like free, bound, or both? Both, right? Yeah, there's no way to separate them. I mean, or say, the easiest way to do this is just measure both.
So what kind of drug does albumin prefer? Hydrophobic or lipophobic?
Yeah, hydrophobic. Yeah, albumin actually has a pocket, which is actually prefer hydrophobic drug. Another interesting thing is actually that pocket, I don't know whether it's designed for that or whatever, but it has very high binding affinity to what is called like hydrophobic acid, like lipid acid. Basically, it does actually have I think residues which can interact with carboxylic acid, but also hydrophobic. So that's actually the pocket. Yeah. But in general, most of the hydrophobic drug latch onto albumin. As you can imagine, basically there are two major ways to eliminate drug. One is through which organ?
Liver.
Yeah, liver, right? And then what else?
Kidney.
Kidney, right? So yeah, so this is feces or urine. So kidney is just a filter, right? Like filter paper we use. And if it's small enough, it's gonna go through. And so the main function for kidney is to block protein stay in the circulation, right? So that's why when you see protein in urine, that means you have kidney dysfunction, right? So that's why small molecules can go through kidney. But then if you think about that, when we take small molecule go into the blood, technically they should just get filtered directly by kidney. They shouldn't stay in our blood. The only reason they stay in our blood because it latch onto albumin. Essentially, the size of that molecule becomes the albumin size, not the small molecule size, right? If you have, for example, one chemo drug is called the gemcitabine. Gemcitabine is super hydrophilic. I don't know. I don't really know what the percentage of unbound. I think that should be very, very high. I know that because we work on that compound before, when we run HPLC using C18 column, there's no retention at all. It comes out just with buffer, so that's just how hydrophilic that thing is. So the gemcitabine plasma half-life is very short. That's why for that drug, chemo drug, you have to do infusion. You cannot just give a single dose because I think the half-life is about a few minutes for gemcitabine. So essentially, you know, if you give a single dose, it's gonna get clear very fast. Yeah, that's why, you know, when compound is hydrophobic, they can latch onto albumin, then they can circulate longer, right? So it's good and bad. The good thing is when you have very high plasma protein binding, you have very low unbound form of the drug. Unbound form drug basically is the one, like you said, you know, work on your drug target, but at the same time, that's also the form get metabolized, right? So eventually it's a balance. When you have very high plasma protein binding, you reduce the unbound form of the drug. Yeah, no question, no, okay. Yeah, I'm going a little bit fast here, but hopefully you guys are okay. I think most people work on this and have some basic ideas here. I mean, generally for these, you know, like pharmacokinetics, the simple ones we deal with like first order and zero order kinetics. But in general, for most of the drugs we deal with, you know, we can simplify it to like first order. For zero order, that generally means you have a lot more drugs than your body can process. You know, so the example for that will be like alcohol drinking, or, you know, because when you drink alcohol, there's a lot of ethanol molecules, right? So you saturate your liver enzyme, or you have like a acetaminophen overdose or something like that. But generally, that's not the case. You know, when you take like small molecule drug, that's the amount you take, maybe like 20 milligrams or whatever. So that's very low. You just remember, you know, most of the cases we deal with first order. Yeah, this is just the thing I just mentioned. We can skip this. All right, so now we are getting into the I would say the key part about this PK stuff. The first one, there are two. Remember, there are two primary PK parameters. Okay, one is this one, volume distribution. The other one is called clearance. So only two. All the other numbers, all the other parameters can be derived from these two primary parameters, okay? And so we call this volume distribution, but see, I have a grayed out word called apparent volume distribution, what it means here, right? So let's just take a very simple example here. Let's say you have 1 gram of drug and you have a beaker and you throw that drug into a buffer, right? And then when you measure the concentration, you know the concentration is about 100 milligram per liter. So the question becomes, how much is the liquid? How many liters of the liquid? 10, right? That's like elementary math, essentially. So you just use 1 divided by 0.1 and you got 10 liters. That's it. That's actually how the volume distribution is defined. So you always remember this beaker example. Basically, what it means is, you know, say, you know, in mice or human, maybe use mice as an example. You inject, like, you know, the dose you inject into the mice. Like generally we do like whatever, say 10 mg per kg, right? And then you can sample the blood right away. You get the blood concentration of that compound. So it's just kind of like, you know how much drug you throw in, you know the concentration now. You calculate the volume of that person or the animal, essentially. Okay. But this number is a hypothetical number. It's not a, it doesn't have true physiological meaning by itself. Why? Because, you know, you can imagine, you know, if you have your drug, if it say only stay in the plasma or blood, then the volume distribution would be the blood volume, right? That does have a physical meaning. But then it also potentially, say you have a very hydrophobic drug, when you do the injection, it can quickly go into your tissue, right? But then when you sample the blood, the concentration will be very low because most of the drug actually go into the tissue. But then if you use a dose, you still keep the same dose, divide by the concentration, your concentration is very low. Then when you do the math, the volume will be huge, right? But that's just the way it is, right? So, but that doesn't really mean that person or the animal has that kind of volume. It's all a hypothetical number. I mean, not hypothetical, but yeah, it's just like, yeah, it's a relationship eventually. Okay. So remember this one. I mean, like I said, always remember the beaker example. You use a dose and then divide by the plasma concentration, right? So these are the two things you can easily know. And then you use that, you can get volume distribution. Just remember the beaker example always. So essentially, the volume distribution is we call this a proportionality factor that relates the amount of drug, which is a dose, to the concentration of drug measured in the biological fluid. Okay, so why we say this, right? I mean, you can sample the blood all the time, right? So you can at time 0, you can at 1 hour, 2 hours, or whatever, and you know, at 2 hours, definitely the concentration will be lower than the very beginning. So then if you multiply by volume distribution, you will know the total amount of drug in the body, right? So that's basically how it works. Yeah. Okay, confused? No? Okay. I think this part is okay, not too bad. So the volume distribution, I mean, it actually can be related to physiological parameters, which we'll discuss later in that. There's another PDF file. We'll go over that together. But you know, just for this is a 70 gram, I mean, sorry, not gram, kilogram person. If you look at that person, the total body water is about 41 liters, right? If you further break that down, you will have extracellular water about 18 liter. And then for that 18 liter, you have 3 liters in the plasma and 15 liter in the interstitial space. And then among this 41, you have 23 in the intracellular space, right? So this is I mean, you don't have to remember this, but I think you should have a general sense. Say in the plasma, we have about like 3 liters of blood, right? Or 3 liters of water. This is basically, you know, you can sort of guess, right? So if you have, like, for example, like this compound, gentamicin, it has a volume distribution about 17. And then if you think about this, that probably means, you know, it mostly stay in the extracellular space, right? So it doesn't really go into intracellular, because if it does, then the volume distribution will be larger. So that's how you kind of use these numbers, right? So you can relate that to the physiological meaning. And like I said, in the the PDF we're going to discuss, I think they have a good examples. Say if you are developing a drug for vasculature, like blood pressure drugs or something like that, you want to have small volume distribution because you want the drug to be restricted in the blood, right? You don't really want this thing to go everywhere in your body or tissue. So that's why understanding the physical meaning of volume distribution is also important. Right, so when you want to have a large volume distribution drug, for most intracellular targets, you probably want to have a large volume distribution. But for the, like the targets in your blood vessel, you probably want to have a small volume distribution. Yeah, we'll skip that. So clearance is a second primary PK parameter. This concept is it's a little bit interesting. I would like to say for a normal person, let's just think this is a beaker, right? So you have all these dots, these are drug molecules. When you have this so-called elimination process, over time, we generally believe the drug concentration decreases. That's why you see these sparse drug molecules, right? That's generally what we believe what happens. However, in the clearance definition, that's not the way it's defined. So what is defined is, you take the initial concentration here, they assume the concentration does not change. But actually that's not true, right? But that's just the way they treat this. They assume the drug concentration doesn't change. But apparently the drug is, removing from the body. There must be something being changed to reduce the amount of drug in there, right? So the way to shrink the amount of drug is to shrink the volume of the beaker, right? So originally you have 10 liters of the beaker, then the beaker start to shrink, and they basically then you have less amount of drug, even you have the same concentration of drug. I know it's a little bit confusing here, but they kind of look at this in two ways. So they assume this thing, you have you either have no drug molecules at all, or you have the same concentration of drug in the volume. Basically, that's how they deal with this. That's why when they say clearance, it's about clearing the volume. It's not clearing the drug, or clear the drug molecule, whatever. So just remember, clearance is to clear the volume, right? That's why the clearance unit is liter per minute or liter per hour. Okay, remember clearing the volume, right? And remember for volume, for the volume distribution is the beaker example, and for the clearance is the clearing the volume. So this is basically the two things I always force myself to remember. So clearance describes the removal of drug from a volume plasma in a given unit of time, right? Drug loss from the body. Clearance does not indicate amount of drug being removed. It does not indicate amount of drug being removed because it doesn't tell you the concentration here, right? Clearance only tell you the basically the volume get removed here. It indicates the volume of plasma from which drug is completely removed or cleared in a given time period. Okay. Good. All right. Yeah, I mean, frankly, I'm going pretty fast, like I think for like lectures generally, I don't go this fast. Clearance is a proportionality factor that relates the concentration of drug matter in the body to the rate of elimination. This is okay. I mean, I don't think you have to remember this one because I don't find this relationship is that useful, frankly. But there's a, so you should, yeah.
So at which time point do we consider plasma concentration for these? Because obviously plasma concentration is changing. So we have just the initial, is there an initial point? Do we use the Cmax? Where do we take the plasma concentration for the clearance rate, or does it matter?
So yeah, that's a good question. So I think this is kind of like in two parallel worlds, essentially, right? So in the clearance world, they don't talk about the changes of plasma concentration. They think you always have this Cmax. Yeah. It doesn't change.
It is strange because,
I know it is strange.
The concentration, we know it's decreasing, but as the concentration decreases, like the volume of distribution will just get infinitely large, right? If we take a dose divided by the concentration.
Well, but no, but here's the thing, right? Because the dose, when you drop the concentration, your dose also drops. So that's why dose divided by the concentration should be a constant. The volume distribution should be a constant.
I see.
From that point of view, right? But from the clearance point of view, they think the concentration doesn't change. What you're clearing is just the volume. I know it's confusing, but I think, frankly, I don't think you guys need to understand 100% at this moment. I think the more, we look at this and the more examples we have, and you may have better understanding, but at least, I think you just memorize what I told you, right? So one is the clear unit volume, the other is the beaker example.
Okay, so plasma concentration used for the equations is probably from the Cmax.
Yeah, for that. Yeah, from to calculate the volume distribution. Yes. So yeah, that's a good question. So for IV should be the C0. C0 means the 0 time point. That's basically extrapolated, right? And that's why a lot of times they don't, like in the exam at least, they don't want to talk about the oral drug because that's you have absorption phase and then what, right? So, but I feel like in those cases they just use a Cmax. Yeah, they assume the absorption is fast. But anyway, that's a good question. The question is with the oral drug, which concentration you want to use, right? I mean, for that, I think you have to factor in the absorption rate, right? Things like that. Yes. You know what? Yeah, I think I have an answer for you because when we go through the calculation, you will find actually for the volume distribution, they don't use the dose divided by the Cmax. They actually use the so-called AUC and AUMC. Yeah. Don't worry, we'll get there. So what?
I don't know, see the other.
No, actually, I can show you. Yeah, I can show you. It's because C0 is not easy to get the accurate number. That's why they don't want to use C0 to calculate all these parameters, because C0 is actually an estimated number. Yeah. Anyway, so for clearance, yeah, you guys always stop me, right? If I have questions. For clearance, it's essentially, we have many pathways for clearance. We have renal, the liver, pulmonary, whatever, right? So all these pathways, they add together will be our total clearance. And for example, if patient have like liver or kidney failure, that means what? The clearance will be smaller or larger than a normal patient. Smaller, right? You lack like one pathway essentially. And then that means if you give the same amount of dose, that means the drug will stay longer or shorter in that person. Longer, right? So that's why for people with this kind of dysfunction, you want to be very careful about the dosing. You want to adjust the dose. Yeah. For example, like when people use this digitoxin, which is actually a drug, to treat the heart disease, and the therapeutic window of that is very small, and you have to make sure, you dose that correctly, you follow the plasma concentration. Yeah, that's actually in the hospital, they do that all the time. Clearance is the other primary PK parameter, and clearance and volume distribution are independent, okay? Independent, not interdependent, independent. Half-life. So we talk about half-life all the time. So what this means, so essentially half-life is for first order PK. So that's the time needed to reduce 50% the drug concentration in blood, right? So in this case, you can see we have 100. After 5 hours, you reach up to 50, right? Then another 5 hours to 25 and so on. And remember, this is the first order kinetics, right? So single exponential decay, and it has a so-called elimination rate constant. We use this Ke, which is elimination rate constant. And if you know the elimination rate constant, you can easily calculate the half-life, which is 0.693 divided by the Ke. 0.693 is basically natural log 2. Okay. And in our later the practice, I'll show you how to calculate this KE based on the log plot, semi-log plot. Half-life is very important for first order kinetics. So different compounds may have very different half-life. Some of them like have minutes. Some of them have like digitalis have about 2 days of half-life, very long. So remember, for first order kinetics, constant percentage of the drug is eliminated per unit time. Okay, so then let me ask you, if you take a drug, right, and initially at time 0, you have like 100 whatever unit, and then after 1 hour, you have 90. Okay, after 1 hour, you have 90. What about after another hour? 81, right? So constant percentage. So it's only 10% loss. So then 10% of 90. That's right. So first order kinetics, yeah, we say this is KE. So what is KE, right? So if you look at this thing, the mono exponential decay, C0 is here, right? So then that's basically the equation for this. It's exponential of minus KET, right? So with this equation, the good thing is if you know the KE, if you know the C0, you can calculate the plasma concentration at any given time, right? So you can essentially solve this equation. And if you take a natural log on both sides, so that'll be natural log T, CT, natural log C0 plus, this minus KET, right? So we call this a semi-log plot. So if you take the natural log on the y-axis, and then time still linear scale, and what you get is a straight line for first order kinetics. Okay, and if you look at this equation, and you can see the slope itself, it should be a negative number, right? So the slope, because it's going this way. But if you can measure the slope, and then you will know the KE. That's the elimination rate constant. That's actually how we calculate this. And in the PK analysis, I don't know why they call this lambda z, but that's just whatever they call that. Lambda z essentially is the elimination rate constant. Yeah. Okay, so any questions here? Let me ask you this. With this kind of fitting, the slope is KE, right? Then what about intercept? The log C0, right? Natural log C0. Yes, originally, I thought they would use this to calculate the C0, right? So, but actually it turns out that's not the case. I'll show you why. Actually, they only use the first 2 concentration data points to extrapolate the log C0, not the full fitting, actually. Yeah, it's the reason for that is because for all these experiments, you have variations, right? So, and I guess maybe sometimes you may not have a very strict first order kinetics. That means you may get, like something like this, right? So like biphasic type of a decay. So if that's the case, maybe at the beginning, fitting with the first couple points, that's maybe give you a better extrapolation to the intercept, then you fit the whole thing, right? So that's, yeah. Does it make sense? So let me maybe just go up here and then we can understand. Say if you have perfect straight line here, and that doesn't matter, you use the first, I mean, you are trying to calculate this number, right? If it's perfect straight line, that's okay, use this two or use, like this 6 points, you probably get the same value here, but that's not a big deal. But if you have something like this, like second order, like this. And if you do the fitting, because you have, all these points here, and if you do the fitting, it will be like here, right? So that's the C0 you predict. However, as you can see, that's not true, because that will be even lower than your first data point, right? But if you use these first 2 points, you get a C0 here. That's actually more relevant, right? Because the point here is the first 2 points may not fall very nicely on your linear fitting here, but definitely the first 2 points are closer to the real situation, right? And to extrapolate to the 0. That's why they use the first data point to extrapolate the C0, not the full linear fitting, which we'll talk about later. But that's I mean, I did this initially, I thought this is a way to calculate C0, but I got the number so wrong. And later I figured they use the first 2 data points.
So basically the reaction is following a mixed kinetics, not really a first order.
Right. I mean, it's hard to have a very perfect first order kinetics, right? So yeah, that's why in reality, they deal with that way. Yeah. I mean, nothing is perfect, right? Yeah, so here are a few relationships, I think, like equations I want you guys know. The first one is easy, the beaker one, right? The beaker example, the dose, the concentration, the volume distribution. This one, like I said, not like super important. I don't really see anybody really to calculate this one. But this is important. This is very important. This is actually, clearance equals to elimination rate constant times by volume. So that's exactly, we say we are clearing the volume, right? The clearance is clearing the volume. Volume is what? Clearing the volume distribution. So you can imagine you have 10 liters and you say my rate elimination, rate constant is like, 1 minute, 1 minute minus 1 right here. So then essentially your clearance will be 10 liters per minute. That's, I mean, just remember, we are clearing the volume and the elimination rate constant, and they multiply together equals to the clearance. We will have more examples for this, but remember this one. This is easy to remember too. You just these are the 2 primary PK parameters, and they are related by the elimination rate constant, and that elimination rate constant Ke, like I said, also called lambda z, which can be fitted in the semi-log plot, right? So the first step for us actually to calculate the lambda z, which is this guy, right? And once you know this guy, and then you can, calculate all these. So
Just one question here. You said clearance and VD are independent, but from this equation looks like they're dependent.
Yes, that's right. Well, or you can think this way. Actually, the Ke is dependent on these 2. I mean, just depends on how you look at this, right? If you put the VD over here, right? So then you can say Ke is dependent on these 2. Yeah. Ke is also the elimination rate constant equals to basically natural log 2, divided by half-life, or half-life equals to log 2 divided by KE. Okay. Yeah. Another concept is called area under the curve. This is an easy concept to understand. It's just, you know, all the area under the curve, right? And to calculate AUC here, I mean, AUC, it's used to evaluate drug exposure, and the unit is concentration times time. So this is the concentration, this is the time, the area. Basically, you multiply them together, right? So you get this. We will talk about this in more details here. One thing is, when you do PK experiment, you do this concentration measurement like here, right? Or say up to here. You can calculate the area by, just use this approximation here. Right, so you can calculate the area here, right? But then another thing is, what about the end? Basically, if you do the fitting, you also have like some AUC, but you don't have any data points here anymore, right? So there's another approximation here. What you do is, they call this AUCs from time 0 to last data point, right? That's how you calculate using these, geometric calculations. But for the last, from T last to infinite, what you do is that you use the last concentration divided by the elimination rate constant, right? The lambda C. That's exactly why they do that. I haven't figured out, but just remember that. Okay, this is actually example data I have from EHI 197, the data we got from Pharmaron. So when you do PK experiment, you will know the time here, you will know the concentration, right? Like nanogram per ml or whatever. So I will show you there's a software or Excel plugin called PK Solver. That's the thing I always use to calculate these parameters. But I'm showing you how to calculate these by hand. Number one is once you get the concentration, the first thing you want to do is to do a natural log of these concentration, you get these numbers. So that's how you convert this kind of linear plot into a semi-log plot, right? So you convert the Y to a natural log. And then what they do is they start to do linear fitting. So for example, can I draw on here? Maybe, yeah. Okay, I can. So for example, like this, right? When you do a linear fitting, so you may have like several points here, like in this case, you may have, oh, you don't see this. Oh, maybe I'm recording this one. Okay, sorry. That's okay. Maybe what I will do, you know what? I think, oh, maybe I can do this one, right? Can I use a pen here? Yeah, like this. You can see now, right? So we can have data points here, 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 and here, for example, right? So what the program does is actually they will take the last 3 data points to do a linear fitting here. Okay, then you can get a R value, right? So it's 0.9907. And then you will take one more data point, you do the last 4, you got like 0.9930 or 09. This is a bigger than the previous one. That means with including one more data point, you get a better linearity, right? You get larger R value. And then you just keep doing this until you reach the Cmax. You can, like in this case, in this case, you do this, you include this one, you include this one, include this one, right? You can see the R value actually keep increasing. That means when you have 6 data points here, include all of them, you achieve the best linearity, right? Best fitting. That's why in this case, they included all 6 data points. But, in certain cases, when you include the first one or first 2, you may have the R value decrease, and then you will just stop there, right? Stop including them. Make sense? That's how the software works. Another thing is that actually, they do this not just based on the R value. They use the so-called adjusted R square value. It's essentially, how can I remove this pen thing? Eraser, erase all ink. Okay, great, cool. So, I mean, you can calculate these R values easily using Excel. I wrote down the equation for you that you can just copy paste. I share the sample Excel. You don't have to copy this, but this is how I do this basically. You can calculate the R value using this equation. But then once you have the R, you can definitely calculate the R square, right? And then the N number is the data points, number of data points. And you can just using the R to calculate the adjusted R square. This is actually how they decide which, how many data points to include. They should see an increase of R adjusted. So N is the number of data points, right? N should be at least 3. You need at least 3 data points, right, to do the fitting. Data points before Cmax will now be included. That's, mostly for oral administration. You may have a couple data points before Cmax. That's not considered in this fitting, right? But for IV, generally, the first data point will be your Cmax. Linear fitting with the largest R square adjust will be used to calculate the so-called lambda z. Lambda z is the slope, right? So that's the linear fitting slope. In this case, lambda z is this number actually by fitting 6 data points in the log C, natural log C versus time 5. Okay. So how to calculate C0, right? Coming back to this question, we already explained. C0 is calculated by assuming a linear relationship using concentrations, natural log C1 and natural log C2 at the first 2 time points. Essentially, it's still like the semi-log plots, but they only take the first 2 data points and then do an extrapolation to the y-axis. Okay, make sense? So remember, to calculate C0, you only use the first 2 time points. And that's how we calculate this. Yeah, in the previous example. Yeah, just the first 2 measure the time points. What time points to measure? Well, yes, that's more like, for the IV, we do like 5 minutes, 15 minutes, and 30 minutes. I mean, if you really want to do a lot, you can do, you can take 1 minute, 5 minutes. It just depends on your experimental design. Yeah. Yeah. It depends on how fast you are, right, to catch that first data point. 1 minute will be super challenging.
Yeah.
Yeah. But 5 minutes is doable.
So for you, like, half-life, you use a C0 or
Half-life, we don't use any of those. Yeah, we'll go. Actually, half-life, we use the lambda z to calculate half-life. we don't use the C0. Like I said, for all these calculations, they try to use the unbiased value as much as possible. You don't really want to, like one value already have a little bit error, then you can propagate errors, right? So yeah, we'll talk about that later. But C0 is just the first 2 time points. Yeah. Yes, I mean, we kind of talk about this one. This is called a trapezoidal calculations. I never remember how to pronounce this word, but anyway, this is so-called the trapezoidal calculation. Everyone knows this kind of, you use this length plus this length times by this and divide by 2, right? So that's all how you calculate the area of this kind of shape, right? So for that, it's okay. But one thing here is, remember, for IV injection, you do need the C0 to calculate the first from time 0 to here, right? To the first data point. So for that, you do need a C0 concentration. That's why, yeah, you calculate the C0 and then you can calculate this area. C0 is used to calculate the AUC from 0 time point to the first data point. Okay. And then we said, what about the last one, right? The one like after your measurements, that's the one we use the last concentration divided by lambda z. And that's how you calculate from the last data point to infinite. And then you add all these together. It's very easy, right? So you can manually do that. So the reason I highlight here is just remember, when we calculate the lambda z everything, we use this semi-log plot. But when we calculate the AUC, we just use this one, the normal, I mean the linear to linear plot. We don't really use the semi-log plot to do that. So in this calculation, the numbers in blue are used for the AUC calculation, basically, right? Right. So for this one, the 772.7 is basically, this one plus this one times by 5 minutes and divide by 2, you got this one, and so on and so forth, right? So you can accumulate this area, right? So you can get the AUC essentially. AUC is calculated on a linear plot using a C versus T. Numbers in blue are calculated. AUC can be readily calculated with sufficient data points. So basically, if you have enough data points, you can get a very good AUC. And to sort of evaluate the quality of your PK experiment, one way to evaluate that is to measure the area from like time 0 to the last data points. So we call that AUC 0 to T last. And then also you calculate the AUC from 0 to infinite, and then you do the ratio. And if the ratio is close to 1, that means you don't miss much of your AUC, right? So basically, even you don't include this T last to infinite, it doesn't matter much. But you say if you stop the experiment here, and then if you do that calculation, you miss a lot of AUC there. That means this PK experiments should be extended. Yeah. So basically, using the ratio, you can just evaluate the quality of the PK experiment. Okay. So that's and another thing is called this AUMC, which is pretty interesting, actually. I never pay attention to this one. I actually didn't know this thing exists before. I mean, I saw this all the time in the PK Sour Excel sheet, but never understand what it means.
One
Yeah.
question here. For AUC, what is the physical
Meaning,
difference of AUC?
well, they say this is related to drug exposure. You just take the meaning of the words, like, yeah. So frankly, I don't really understand this very well. It's
So describe the overall, the drug concentration. But also,
not just the concentration, also time,
yeah, the overall, the whole time,
right? Whole time.
yeah.
So to go back, actually, to rephrase your question, why this AUC is important, right? So interestingly, some drugs, the efficacy depends on AUC. Some drug depends on the Cmax or the concentration. So it's all like related to pharmacology. I would say for most of drugs, actually, they're more likely to be AUC dependent. But there are definitely certain, especially like like anti-infection drug, like bacteria stuff drug, because they have so-called minimal inhibition concentration, right? So as long as you have the drug concentration over that concentration, and then you are good, right? So in that case, the concentration becomes very important, not the AUC. But yeah, even for the the antibacterial drugs, some drugs actually is dependent on AUC. I don't know, actually I asked my wife about this and she told me just remember that. But they do use, I think for vancomycin is AUC related, but for certain drugs it's concentration related. But anyways, I think at the end of the day, so then the question becomes, how do you know it's AUC dependent or concentration dependent, right? So that's a legitimate question. The way they figure this out is they do this so-called fractionation dosing. I actually asked this question to a pharmacology person. There's no way to figure out by doing in vitro experiments, essentially. And what they do is, what is fraction dosing? So say if you give the drug 10 mg per kg every day, okay? And then you achieve, like a PK curve, something like this. Alternatively, what you can do is you can split the dose into 2 doses, like 5 mg per kg at time 0 and then 12 hours. So essentially, you still in the same day, you got total dose of 10, right? But you split them into 2 parts. So essentially, when you do that, the AUC doesn't change. You sort of split the AUC, but your peak concentration change because you only have half of the initial dose. So then you compare the pharmacological outcome. If the outcome is the same, that means it's AUC dependent. If the outcome is different, for example, the single dose is better than the split dose, that means more likely to be concentration dependent, right? So which means you have to hit a minimum threshold of the concentration, otherwise it doesn't work. That's how they figure this out. Okay. Yeah, so now is this thing, AUMC. What the hell is this one, right? So this one, I try to look for the meaning of this physical meaning. Later, I dig into those very old papers. This is, so, well, let's take a look at the definition. Definition of AUMC. AUMC, the full name stands for area under the first moment curve. Okay, what it means, I don't know. But the definition is basically the y-axis is the concentration times time. See, this is basically the AUC, right? Now they plot AUC against time. Kind of, right? I know it's confusing, but anyway, for the expression, it's easy to understand. You use the concentration times by the time, then you plot against time, right? So that's the AUMC. This thing is actually, like I said, this is based on a theory called a statistical moment theory. What it means, I don't know. but that's the theory, I think this is something people use in engineering and they adopt that concept into the PK analysis. And why they do this, I don't know. And how they derive all this, I don't know. But this is how they do this. They use this AUMC. So why they do this? Because these AUMCs can also be easily calculated, right? Why? Because you can basically just all your concentration and the time, and you just multiply them together, right? Then you can do this plot, and you get this so-called AUMC plot. That's very easy to do. When you do that, see, this is interesting, right? So in the AUC, we have to know the C0 because we need to know the first approximation there. But in this case, you don't have to know. Why?
Because time zero.
Yeah, time 0 is 0, right? So you multiply it's 0, so you don't have to know. So that's a good thing about this one. And so this 0, right? So the first one is a triangle. So then later you do this, the tri, whatever it's called, trapezoidal, right? Yeah. So you do this approximation, you can calculate the area. So, the bottom line here is for the AUC, you can manually calculate. For the AUMC, you can also manually calculate. So these two numbers, you can reliably or say easily get that mathematically based on your raw experimental data. Okay, so these basically, remember, the AUC and AUMC are the numbers we can get reliably. That's why a lot of the following calculations are based on AUMC and AUC, not based on, like other things. And for the same reason, for AUMC, you can easily get from time 0 to time t last, right? The last data point. What about the things after that, right? So this is the equation for you to calculate after that. You use the last time concentration times by t last and divide by lambda z and plus this, lambda z square, whatever. So it's easy. You just follow the equation. Exactly how they derive this, I don't know. But in Excel, you can easily calculate AUMC following all these equations. Okay. Yeah, I think we are getting through most of this. So now with AUC and AUMC, we can calculate a parameter so-called mean residence time. Mean residence time represents overall persistence of the chemical in the body, is the average time that species stay in the body. This thing is basically, we call this half-life, but in the fitting, there's actually, I think maybe you guys also heard about lifetime. When you do, like, when I was a graduate student, I did like tons of these fittings. We don't really calculate half-life. Actually, we calculate lifetime of a species. Lifetime essentially is 1 over the rate constant, 1 over Ke or 1 over lambda z, right? So that's the lifetime. Not like log 2 over Ke, just 1 over Ke, and you get the lifetime. And that's essentially, the lifetime is just the so-called mean residence time. Yeah, mean residence time is just how long the molecule stay in that body on average. It's just essentially, related to your half-life, right? So the difference there is just log 2. But, like I said, this MRT can be directly calculated using AUMC over AUC. Why that happens? Yeah, I don't know, but that's the way it is. Yeah, you know how this derived?
I got CPD,
What?
well,
CPD? What did you?
like AUMC in the y-axis, you have CPT.
Yeah, CP times T, yes. And then
for
divide by
AUC,
the
you have VCP,
CP.
or something like that.
Yeah, maybe, yeah. But then exactly how the math works, I don't know. But anyway, we don't have to know all the details. I think as long as, we understand most of the parts, so we are okay. And this is the way it is, right? And another way to calculate the KE or lambda Z, yeah, so you can do this. You can also use the lambda Z to calculate this MRT. But like I said, this is generally how people do this, right? AUMC or AUC. It's mostly because these numbers are less biased, basically more reliable. And then with that, you can do a lot of calculations here. Actually, how they calculate clearance. They actually do this dose divided by AUC. So AUC is known, dose is absolutely known. That's whatever you put into the mice. Divide by AUC, you get the clearance. That's how they calculate that. Then how they calculate the volume distribution. There are two, they give two types of volume distribution. I think this one is they call that VZ. Z means, I think that means lambda Z. So it's more like elimination related volume distribution. And so to calculate that, it's just use the clearance, right? Remember we said clearance equals to KE times by volume distribution, right? So essentially, if you know the clearance, you divide by the elimination rate constant, you can calculate the volume distribution. Another way of calculating this so-called steady state volume distribution is using the clearance times by MRT. MRT is essentially 1 over lambda Z, right? But I think the difference here is, the steady state volume distribution, you can calculate using this way, basically dose times by AUMC divided by AUC squared. This is basically, dose divided by AUC equals to clearance, AUMC divided by AUC equals to MRT, right? So you can essentially calculate the steady state volume distribution using 3 unbiased numbers, essentially, or least unbiased numbers. That's why a lot of the the reporting, they report this steady state volume distribution. They don't report this one. Yeah, because this is based on, clearance is calculated from here, and then this is based on fitting. So, you may propagate the errors, but this is probably more reliable. But if you look at the calculations, if you get a good PK curve, these two numbers are essentially the same, not much difference. So yeah. And then to calculate the half-life, you use log 2 divided by the elimination rate constant. That's how you calculate the half-life. Okay. This is the equation.
They're all first order points, so we're assuming that the counts are principal constant. So that's why they are concentrating independent.
Yes, you're right. Yeah, we just assume all these are first order. Yeah. Okay, good. Chen, you have some homework, you better understand. I have things for you to do. Okay, so hold on. Wow, so it's been like 1 hour already. That's pretty long. But I wanna go over this thing. Let's see. Maybe I can stop the. Ooh. Yeah, I'll stop the
In terms
PowerPoint.
of doing experiments, people only do one experiment, and we can get all this data, like this.
Yeah, one experiment. All right.
question, actually.
Yeah.
It's, when you calculate the elimination rate constant, and you start from the end of the semi-long block, right? And it said, take like 3 points and keep going.
Right.
Until
You don't improve the
yeah,
linearity.
you want to maximize the
Right.
R squared value,
Right.
right? But does that mean we take all these points and just remove the points that reduce our R squared value, or you just keep going until you stop? Because experimental data, you may have some variation, right?
What do you mean remove?
Well,
So
okay,
you get rid of the,
Is it directly, I go 3 and then it improves, but then maybe it decreases, but then maybe it increases again?
Oh.
Do I only take out that point that decreases, or do I stop there and that's?
you
all
stop.
there?
Once you decrease, you stop. That's how the software works.
Okay, because
Yeah.
I'm thinking, you know, maybe there's some variation in the experiment where you have a data point.
Time point, which is bad, right? Yeah, I don't know. Yeah, I mean, that's basically how the software works. They will stop once they see drop of the R square value. Yeah, yeah. But in reality, you may manually just take that data point out and then do the analysis again, right? Yeah. This one is actually another PowerPoint, not PowerPoint. Yeah, it is a PowerPoint I found online. It's very good. I personally benefit a lot. This is a director from BMS. He gave a lecture on the PK consideration of drug design and development. This is a lot more in-depth than the thing I talk about. So they just show, over the years, the problem for PK decreases because, people understand this a lot better now, right? So yeah, that's not, we don't have to worry about this one. Yeah, primary PK parameter, clearance of volume distribution, secondary PK parameter, half-life and bioavailability. So they talk about the bioavailability here too. Right, so yeah, basically, when you have drug in circulation, it either gets excreted by kidney or get metabolized by multiple routes, essentially, or it can be distributed into tissue. Oh, too fast. Yeah, so these are the parameters. Another important thing we didn't touch on is this protein binding, right? So the U means unbound, right? So the fraction unbound, that's important. And F means bioavailability. These are the things we didn't talk about. So clearance concepts. I mean, clearance can go through all these different pathways. And this is the same thing we just talked about. But in practice, in practice, clearance equals to what? The dose, IV dose divided by IV AUC. So they said need to dose IV to estimate clearance of compound. That's actually exactly what we are doing, right? So we do IV injection. That's the only way you can accurately estimate the clearance, right? So then for oral dose, clearance divided by F, which is the bioavailability, then equals to the dose of PO and the dose of AUC. But you have to measure the clearance in IV injection to be able to get the clearance. And then you can see, then you get this one. You can actually think about, you divide this first equation over the second one, you get F actually equals to what the ratio of this one over this one, right? That's how you calculate the oral bioavailability. Yeah.
Maybe this answers my earlier question. Like maybe you need that C0 and then Cmax isn't valid. And they say you need to dose it IV. Maybe they can't do it for an oral drug.
Yeah, you have to do IV to get this clearance accurately. Yeah. For oral, it'll be more complicated. So they say effects of a change in clearance on plasma concentration time curve. So for a high clearance drug, you have like something like this with a short half-life. Low clearance drug, you have something like this. Right? And see, half-life changes in reverse proportion to clearance. Decrease in clearance results in proportional increase in half-life and vice versa. But clearance is the only parameter that affects both half-life and AUC. Yeah. Well, I guess, you know, so later we will see actually volume distribution only affects the AUC. Is it AUC? Yes. Yeah, but anyway, yeah. Yeah, this is another interesting thing. I think all of us should know. So-called organ clearance and extraction ratio. What it means. Basically, you know, the way it works, we have the blood, you know, flashing through the liver, right? And there's a flow rate. And the reason they call this clearing the volume, because you have to have this, you know, I would say the fastest clearance will be, you know, you have this blood going through the liver, you know, before the liver, you have drug molecules in there, but after liver, you got nothing in there. That means the clearance rate essentially equals to the blood flow rate, right? So that's why, I mean, that's why they develop all this clearance concept. So the clearance equals to blood flow, they use Q times by extraction ratio, or they use clearance divided by, you know, Q, that means the extraction ratio. So you can just think about the maximum, like for example, if you look at the data, in mouse, the liver blood flow is, I think it's 90 mils per minute per kilogram. That means when you measure the clearance CL, it cannot be larger than that value. Otherwise, it'll be wrong, right? That's the maximum value you can get. And if you look at all the data we have, that's just spot on, you know, pretty much. We have like the bad molecule we have, it has about like 80 mil per minute per kg. And some of the good ones we have like, you know, 10, something like that. So just remember, you know, you cannot have the clearance larger than the blood flow value. Yeah, see, this is the blood flow, right? For mouse, we should remember this number 90. So that's the max we can get. And for a human, it's 21. Okay. And generally, for a stable compound or low extraction ratio compound, they use 0.3 as the cutoff. That means 0.3 means what? In mouse, you should have the clearance less than 27, right? And in human, you should have less than 6.3 as the clearance value. If you're larger than that, that means the extraction ratio is greater than 0.3. They consider high clearance drug. Okay, yeah. This is, you know, this is good. Help me to understand how we look at these numbers. And so for high clearance drug, it's, you know, like larger than 0.7. That's called high clearance drug. For what? No. For drug that undergoes hepatic and renal clearance, right? So clearance will be like the total of hepatic clearance and renal clearance. For this one, I think, you know, we really, so you need to use those so-called metabolic cage to measure how much actually go into the feces, how much go into the urine. You know, Feng Li actually, he has those cages. You know, maybe at the point we want to do that, we can use those. It's you just put the mouse in a cage and then feed the drug. So, there's a thing to capture the urine and capture the feces after 24 hours. You can just do LCMS analysis on that to know how much drug in there in each component. And then they said, with all the understanding of this in vitro, like, we do S9 all the time, also do the primary hepatocytes. Then they said you should build a so-called in vitro in vivo correlation to further optimize the in vivo clearance. But, I also read some papers, they did analysis. Basically what they say is it's very difficult to use in vitro to predict in vivo. And I kind of feel that's the case. At least, I'm going to show you some of the analysis I have, maybe like here, just quickly. We don't have a lot of these, but at least if you look at these 6 compounds, we measure their IV PK. We measure 10 of these EHI compounds. And also 6 of them, we have this primary hepatocyte data. Based on primary hepatocytes, we can get the so-called intrinsic clearance, right? So then you can see this is pretty much random. There's no good correlation at all. So that's why, I feel, I don't know, I feel there's not a lot of value of doing all these in vitro experiments, especially now we have our own triple quad, and if we can do this in vivo profiling, they will be a lot more valuable than the in vitro experiment. I think Dong has a poor experience with this, and he tried very hard to optimize in ICE9. He got like super stable compound, but then in the PK is essentially the same, not much improvement there, just slightly improvement. So it's okay, but anyway, they say they do that in industry, but I think we probably wanna just use in vivo. In vivo clearance could be predicted from in vitro microsome. I don't really know, but that's that reliably predicted. Volume distribution, VD. Volume distribution amount in the body divided by plasma concentration, right? This is the apparent volume. We talk about this one. We talk about the beaker example. We can skip that. It's that volume distribution scales very well with body weight. So similar volumes for preclinical animal species. That's understandable, right? So because we have compare with mouse, we just have different weight, but probably the composition is very different. It's the same. You have tissues, we have blood, right? So yeah, T-half changes in direct proportion to volume distribution, but change in volume distribution does not lead to change in AUC. That's why, but for clearance, when you change clearance, you change both half-life and AUC. But for volume distribution, you only change the half-life, you don't really change the AUC. But anyway, that's just yeah, this thing is interesting. Actually, this is something I learned new. See, this is the number we can calculate from the PK, right? So that's the volume distribution steady state. But that equals to, so they said this volume distribution can be related to true physiological volume. It means, the volume of the plasma and the volume of this total tissue water outside the plasma. These numbers are known based on the weight of the person, right? And also you calculate, you can know the unbound portion in plasma. That's something you can measure. But I don't really know how you can measure this one, unbound fraction in tissues, because you have so many different tissues. But I guess if you know this number, you know this one, you know this one, you know this, and you can calculate this one, right? The unbound portion in tissue. That's the physical meaning of this. this thing. They said when volume distribution is smaller than 0.3 liter per kg, a drug is considered to have a small volume distribution, indicate the drug can be highly protein bound in plasma, so they do not distribute to tissue. When this is desirable for extracellular targets or vascular targets, right? So that's when it's desirable, highly plasma bound. But when you have very large distribution, drug is said to have relatively large distribution, indicate drug distributed outside the vascular space, maybe well distributed in the body, or may not distribute through the body, but only concentrated in certain tissues. But that, anyway, it doesn't, stay in the blood a lot. But it's good for intracellular target. For a lot of the compound or the target we'll work on, like ICH, kinases, these are all intracellular targets. So we need to have a large volume distribution. Yeah, we can just skip this. Half-life, we know, right? Half-life, it's we can calculate using log 2 over the clearance rate constant. So we can skip that. This yeah, so half-life between 10 to 20 hours enable once per day dosing. That's ideal. But compounds with short half-life, 2 to 3 days, require frequently daily dosing. Extremely long half-life is problematic. Also useful for calculating extended accumulation following multiple dosing. Half-life enable estimation coverage over a dosing interval. Yeah, but anyway, I think generally this is the number people shoot for, like 10 to 20 hours, so they can achieve like single dose every day. But still, like a lot of antibiotics, they don't have very long half-life. Then we just take them, like even some of them every 4 hours, right? So it just because of the half-life is short. Yeah, but if we can achieve this kind of number, that's great. Bioavailability, like I said, this is, you can consider this as dose normalized AUC, right? AUC of oral divided by the dose and over AUC IV divided by IV dose. So this is kind of like dose normalized AUC. Essentially, if you give the same dose, these are canceled out. So basically the AUC for the oral over the AUC for the IV, then that's the oral bioavailability. That's how you calculate that. Okay. Easy, remember. Yeah, then this thing is also important. I think this is something I learned new. What determines oral bioavailability? So there are 3 parts contributing to this. Once you give the drug, it will go into the gut lumen. So it has a first absorption process, right? It can be absorbed, can be, like not absorbed. So there's only FA fraction of drug get absorbed. And then it needs to go through the gut wall. Through that process, you can also get metabolized. So only say you have FG% left. So then FA times FG will be eventually whatever you have left in the portal vein, because once it will go into portal vein first, right? Once you go into portal vein, there's a third process, which is the liver, right? So the liver going through that, you have FH% of the drug go through the liver. The rest will be metabolized. So eventually, after all these 3 processes, you get into this systemic circulation. So the total bioavailability equals to, these 3% times multiplied together. Okay. It's just very hard to measure these values. With PO dose, you go through all these 3 processes. But if you give a portal vein dose, I don't really know how easy to do that, but apparently people do that. I think it's a surgery process or whatever. But if you do that, you can measure the bioavailability And then you will know the you'll be able to calculate FH directly. And then from there, you can calculate the FA times FG, right? If you know the FH. But it's a challenging experiment, I guess. You know, that's how people measure that. If you really care about this, I think it will be pretty intense experiment. So another thing is the unbound portion protein. So the unbound free drug hypothesis, right? Only the unbound form is the important part, and the FU equals to what? Unbound drug concentration over total concentration. See, this is a table, or I mean, not the table, statistics of 62 compounds developed by BMS or drugs. See, a lot of them actually have very high plasma protein binding. They have only 1 or 2% of free. So what it means it doesn't matter you have a high plasma protein binding drug. At the end of the day, you know, the it will show you later when in the calculation, it will cancel out, because when you have a high plasma protein binding drug, you will also reduce the metabolism. So it goes both ways, right? It will reduce your efficacy on the target, but also reduce your metabolism. So it goes both ways. So at the end of the day, the most important thing is to reduce drug clearance or the metabolism. That's the important part. That's why they say, you know, when you optimize the drug, you shouldn't focus on the plasma protein binding. That's not a good parameter to optimize for. You should still focus on the clearance, essentially, stability of the compound, and also potency.
So did they compare these, the FU to the marketed drugs?
Yeah, I don't think they, I mean, this one, they only did this one, they only BMS. I think there are definitely analysis on this. I know a lot of drugs, a lot of compounds, they have highly plasma protein bound. But I think that data should be available somewhere. We can check it. Yeah. Yeah, see, this is basically now you get this FUP here, right? That's how you related this plasma protein binding and the volume distribution coming back here. They also have this thing. So this is basically clearance. They can also calculate clearance using the blood flow, right? The QH is the hepatic flow, which we can check the table. And the FUB is this unbound form, right? In the blood, unbound percentage. And the intrinsic clearance, they calculate the intrinsic clearance based on this microsome studies, essentially, or hepatocytes. But you know, I'm thinking if that's the thing is those in vitro experiments are not accurate, then using those to predict clearance probably is not that accurate anyway, right? So you have errors here and then it's gonna propagate. So I don't know, maybe for us, since we know the clearance already, maybe you can, yeah, I don't know, maybe it doesn't matter, yeah. Well, if you know the clearance, you know all these numbers, you can calculate the intrinsic clearance. So for drug with low extraction ratio, the clearance equals to FUB times by intrinsic clearance. Low extraction ratio, that means you have stable compound, right? And but for drugs with high extraction ratio, the clearance equals to the blood flow, essentially. Independent plasma protein binding now. Right, so that means this number is large, very large. No, I mean, clearance. Oh, sorry, this one is large. So, okay, clearance is very large. That means in this, both of these, so FUB times ICL intrinsic will be much larger than this one. This can be omitted. So then if you do the math, these two cancel out, CL equals to QH, right? So that's why for high clearance drug, that's why CL equals to QH. For low clearance drug, this one is small and then the QH cancel out. So that's why CL equals to FUB times CL intrinsic. That's how they calculate this. Okay. For low extraction drugs, yeah, I think these are, I don't know whether these are that useful. We can just maybe skip this one. Yeah, here. I think this is important, something we should, this is pretty much the last slide they have. Common misconception. When plasma protein binding is reduced, increased unbound concentration will cause increase in drug effect and potential toxicity. They said focus on drugs administered orally and cleared by liver. What they mean here is efficacy is determined by at the active site. So see, if you do the AUC for the unbound portion of AUC, right? So, well, for the AUC oral, it's it means the FA times, well, AUC oral is, this is F times dose over clearance. And then how they come here? Oh, for low extraction drug, clearance equals to this. But then where's FH? Oh, FH, okay, here, FH equals to this 1 minus extraction ratio, right? So why is 1 minus extraction ratio? Because FH is the percentage of compounds actually survived through the liver metabolism, right? The ER is the one get destroyed. So that's why 1 minus ER extraction ratio equals to FH. And then they equals to this whole bunch of things. And then what clearance equals to this. Anyway, you guys can go back and think about this, but
That's related to how you're saying that some of the drugs were AUC dependent and some were not, some were concentration dependent. When isn't this saying that the AUC is independent of the plasma protein bar?
is that AUC is independent of a plasma protein binding. No, AUC is actually, see, AUC, total AUC is dependent on the plasma protein binding unbound portion. But the unbound AUC, which is the one you care about, right?
Okay.
Unbound AUC is that's what you care about. It canceled out, actually. It's only depends on the FA times FG and, the dose over intrinsic clearance. So that means, from this point of view, actually it's important to calculate this CL intrinsic. I think we can easily calculate that because we know the CL, we know all the FUB, and we can calculate the CL intrinsic because that will help us to calculate this, the unbound AUC. Or unbound AUC, actually, you can easily calculate that with AUC times by the unbound percentage, right? So if you know this one, you know this one, and then you can calculate the FA, FG. Anyway, I think we can, yeah. So what I want to do next is we just do a practice and use our EHI compound. We calculate all these parameters, get as much information as possible from this. Just follow them. Is that go beyond AUC effect on FU on PK profile for low clearance drug. For low clearance drug, see, they said, I think this is important. for low clearing drug, right? They try to tell you exactly for a small volume distribution compound, you actually for this small unbound portion, actually you get higher drug concentration. Decrease unbound C-CHOP for compound with small volume distribution. Decrease unbound. Yeah, that means, you know, this is why. Let me see. No change in unbound AUC and C-CHOP. I think I understand this yesterday. No change in unbound AUC and C-CHOP when with decreased protein binding. Unbound AUC and C-CHOP. Let me see. No, I think that's large. Okay, see, with large volume distribution, essentially, no matter you change the, unbound fraction, the AUC and also the C-CHOP. C-CHOP is the lowest concentration right here at 24 hours or 48 hours. It doesn't change for large volume distribution. That's basically how they get this. But with small volume distribution drug, with basically AUC doesn't change, like it's just this one is more flat, but this one's, more deep. But, this I'm with more unbound drug, FUP equals 0.5, you have lower C-CHOP. That's why they say decrease unbound C-CHOP for compounds with small volume distribution. Okay. Anyway, that's just a conclusion here. That's all. Yeah. For all this. Okay, guys, do you have any questions?
I'm wondering what the utility of the multi-compartment models is and how much more complex these are than the one compartment model.
No, these are all so-called non-compartment models. We don't, that'll be another discussion for the compartment models.
Yeah, but what's their utility?
They just should be more accurate to reflect the PK. I think to get better understanding. Yeah, but for our level, non-compartment model is more than enough. Yeah, we are not that sophisticated. So just quickly, I know we already stay here almost 2 hours, but I uploaded this PK solver in the ADME channel. So what you do is you can double click this one. Unfortunately, this is Windows only software. That's why I think you should use Windows. Yes, okay. Then, let me see. Uh-oh, I hate this thing. How can I get rid of that? How can I hide this thing? Hide video panel. Oh, okay, good. Okay, now we get this one. So it's very easy to show you how to use the solver. You can copy paste these raw values right into an empty sheet here, essentially. Then you go to add in PK solver. And we are doing non-compartment model IV bolus, right? And then you just choose a time, which is like from here to here. You choose a concentration from here to here. So these are actually 3 miles, right? And then the time units, we have minutes, and the concentration units is nanogram per ml. I don't know, our dose was our dose was mg per kg, I think 0.5, 0.25 mg per kg. Yeah, then you just click run. See? All right. Compartment analysis successful. They will generate all these tabs. Actually, they give me 3 new tabs here, PK3, 4, 5. Right, so if you look at PK3, this is essentially, you just follow what I said. That's actually how they calculate all these. And they use these 6 data points to calculate. But you can easily, you know, get this here, get all these numbers, C0, so on and so forth. Yeah. One last thing, you know, I wanna, there are too many things. I look at this, our data, essentially, these are the data chain collected in the Excel. I just pick the one with reliable values. And then I calculate, because we have this 5 minutes and 1 hour brain concentration, plasma concentration. I just use these 2 data points to calculate this lambda C, essentially the elimination rate constant, right? Using a log normal plot. And this is what I got, actually. This is totally what I got. But there are 3 outliers, 285, 263, 264. If we remove these 3, this is what I have. You can see, you know, essentially the plasma elimination or the brain elimination is correlated to the plasma, which makes sense. Essentially, you know, for compounds which are not PGP substrate, that means once your blood compound is gone, you know, the compound gonna diffuse out from the brain and then get eliminated, right? If you have high concentration in the blood, they will stay in the brain. So I think that part, this is something good, at least for our EHI compound. Another thing, then the question becomes, you know, for this one, how we should design the experiment. Right now, we are doing the experiment, we are doing this 2 data points experiment, right? So we sack the mice, we do IV, sack the mice at 5 minutes, do IV again, sack the mice at 1 hour, and then we use these 2 time points to estimate the clearance, right, in both brain and the plasma. But apparently 2 time points may not be very accurate to estimate the clearance, right? So you may have errors there. I want to hear your opinion here. You know, I'm thinking what we can do here is we still do the 5 minutes profiling for the blood and brain, but then we do another group of mice. We just do the IV injection. Then we don't kill them. We just draw the blood at 3 time points. We don't have to. So basically, we only take 10 microliter blood, like what you have been doing now. But good thing for that is you can keep drawing blood from the same animal, right? So for that, you don't get animal variation, and the PK profile from there should be more reliable than you know, than you get from different animals, right? Does it make sense? Well, I think I'm running low on the battery, but let me, okay.
But then brain is also there. How do you want to do the brain?
What do you mean? How do I want to do the brain?
I mean, blood, you can.
Every 5 minutes.